NP-hard and NP-complete problem. It is one of the most important topic in design and analysis of algorithm. In this video, we will discuss about the basics of NP-hard problem, NP-complete problem, and also we will see how to convert from NP-hard problem to NP-complete problem. To start with, if we remember the various algorithms that we have studied during the DAA course, Design and Analysis course, we have found few algorithms that is with linear time like order of n. One example is linear search algorithm. Few of the algorithms are there with order of n square like bubble sort algorithm, insertion sort algorithm. Also, we have logarithmic time algorithm like binary search, merge sort, quick sort. These are the algorithms with logarithmic time. And also, we have another set of algorithms where the time complexity is order of 2 to the power n or 3 to the power n, power of n. So, where n is the size of data. If we see the graph for computation time and the size of, this is computation time and this is size of n or the size of data, then we can see that the order of n square or order of n, this kind of algorithms grows very slowly along with the increase in number of data. But however, this exponential time complexity, the algorithms with exponential time, it grows very fast. In this type of algorithms, for a very small value of n, let's say n equals to 20 or n equals to 30, execution time of the algorithm is too high, which is not possible to execute in real time. So there is always a tendency to find out algorithms which is better than exponential time complexity. For example, if we consider the 0 by 1 knapsack problem where time complexity is to the power n, our main objective is to find an alternative algorithm, say alternative algorithm A, where time complexity will be not in exponential but it will be in polynomial time. So that is the main objective of this topic. The basic idea is if you have a complex algorithm with time complexity of 2 to the power n, we try to find out another algorithm for this so that we can compute it in polynomial time. That is the primary requirement. However, in order to go into the deep of the topic, we will first discuss certain background. For example, we'll start with the explanation of a deterministic function or deterministic algorithm. We'll go for non-deterministic algorithm. Then we will go for complex problem. Then we will discuss what is a hard problem. Also, we will follow up with the explanation of NP hard and NP complete problems. So these are the topics that we will be covering in the entire video. So let's start with the discussion of the deterministic algorithm to understand the basics of NP hard and NP complete problem. To understand the deterministic and non-deterministic algorithm, let us take an example. Here, this is the example where we are taking a function of linear search. This is the linear search function. It takes one parameter x, and that x is searched in the array A for n number of elements. And if it finds the element in the array, it returns the position where it is found. And this is the driver code for the search program or search function. And we are calling this function search with the value of x and value of a. These are the values of a, and x is given as 30. So 30 will be searched in the array. If it is found, then it will return the position, otherwise it will return -1. Now the time complexity of this algorithm is mainly dependent on the search function. So when we want to compute the time complexity, actually we compute the time complexity of this search function, which is order of n. This is the time for linear search. because here there is only one for loop, and this one for loop is executed for n times. That's why it is time complexity is order of n. Now let's say we have defined one function, say my search. For example, my search, it will take the parameter x, and also it will take the parameter array, and also number of elements, and we assume that this function will complete in order of one time. But problem is we do not know how this my search algorithm will find the element in the array in order of one or constant time. That we do not know at this moment, but I am claiming that I will be able to find out a function which will search the element, given element x in the array in a constant time. Here, instead of search algorithm, I will call my search algorithm, with all the values x, a, and n. Then this will be computed in order of 1. Now the time complexity of this algorithm becomes order of 1, which is a constant time, and it is much better than that of order of n. The problem is, actually at this point of time I do not know how this will compute in order of 1. That means I am assuming that in the near future I will find an algorithm which will find the element in the array in a constant time. So this is this statement where actually we do not know at this moment of time, and we will find out in a later time, maybe after 2 or 3 years or many more than 10 years. Then that will be useful, or that will be a practical scenario in the search process. So since we have included this type of algorithm, then this kind of functions are called non-deterministic function. And whereas in the earlier case, if we use the search algorithm, this is we know about the search algorithm, and it gives the time complexity of order of n, and it is well established. So in this case, in the previous function, this is called a deterministic algorithm, or deterministic procedure. This is a deterministic when we use the standard search approach, and this same algorithm is non-deterministic when we use a different algorithm whose execution is not sure at this point of time. So that is considered as non-deterministic algorithm. So here the my search algorithm, it computes in order of 1. The time complexity of this algorithm is order of 1, and this algorithm is a non-deterministic algorithm and gives a time complexity of polynomial time. So that is why this algorithm, my search algorithm, where we have some undeterministic statements, is called non-deterministic polynomial algorithms. Now we will explain how these non-deterministic algorithms can be used for solving complex problems. Generally, one question comes to our mind, where to use these non-deterministic polynomial algorithms. Previously, we have seen that there are a set of algorithms whose time complexity is exponential, that is 2 to the power n. And this set of algorithms are not possible to implement in real-time scenario. That is why we also said that we need some alternative of this kind of algorithms. And those alternatives are supposed to be of polynomial time. But however, writing directly a polynomial algorithm for this kind of algorithms or this kind of problems are not possible. Here we make use of the non-deterministic polynomial algorithms. What we do, let's say if I consider 0 by 1 knapsack problem, then we have a solution to the power n, and for this problem we will write one non-deterministic polynomial algorithm, and we will assume that this works better than the existing exponential time complexity algorithms. So here, but however, few of the steps here or few of the statements in this algorithm will be non-deterministic, and we will find out the solution for those non-deterministic statements, and finally that will be acceptable to research community. So that is why the non-deterministic polynomial algorithms are useful in order to find out the alternative algorithm or polynomial time algorithm for all those problems where we have a exponential time complexity. So based on that, now we will see the concept of NP hard problem, NP hard problem, and also NP complete problem. Now we have a set of algorithms with computational time complexity of 2 to the power n or factorial n, either 2 to the power n or factorial n, and these are called the complex problem. Let's consider that these are complex problem or these are hard problems. We need to find out alternative algorithms for these algorithms which gives a time complexity of polynomial time. That is our requirement. These kind of problems with polynomial time complexity will be in number of hundreds or number of thousands and more than that. That is why writing individual non-polynomial algorithms for each of the problem is little difficult. People try to solve any one of the problem first, and then rest of the problems are somehow transformed to the previous problem. So if now I have a solution for this traveling salesman problem, and I can relate the Hamiltonian cycle detection problem to traveling salesman problem, then since traveling salesman has a NP non-polynomial algorithm, that is why we assume that Hamiltonian cycle detection also has a non-polynomial algorithm. So this is the approach, and for that what it is done, there is a standard benchmark problem, and that benchmark problem is known as satisfiability problem. For any three Boolean variables x1, x2, and x3, we devise one conjunctive normal form equation or Boolean equation as x1 or x2 bar or x3, and this is one part of the equation, and x1 bar or x2 or x3 bar. So this is a conjunctive normal form. Then the problem states that we need to find out the values of x1, x2, and x3 such a way that the value of the equation it evaluates to a truth value of true. We need to find out all the solutions, and also the value, since x1, x2, and x3 are binary variables, that's why they can take either a value of 0 or 1. Then we need to find out various combinations, and this problem, let's say possible values are 0 0 0 0 0 1 0 1 0 0 1 1 and till 1 1 1. So here for three variables we can have a total combination 2 to the power 3 which is equals to 8, and for n number of elements we'll get a time complexity, or we'll have a time complexity of 2 to the power n. Now since this problem, the satisfiability problem, also has the time complexity 2 to the power n, that is why the satisfiability problem can be considered as one of such problems listed in the list of complex problems. Now, if I can solve the satisfiability problem in terms of a non-polynomial algorithm, and if we can transform the traveling salesman problem to satisfiability problem, is also considered to have a NP algorithm. So this is the method how we relate these two problems, one benchmark problem and other any existing problem in this space. One important thing is this satisfiability problem is a well-known problem, and it is a NP hard problem. NP hard problem. This is established NP hard problem. Also, it has a non-polynomial algorithm to solve this problem. Since it has a non-polynomial algorithm, that is why this problem is known as NP complete problem. So any problem L which is actually can be converted into a satisfiability problem, then L is also called the NP hard problem. Then apart from that, if I can construct one non-deterministic polynomial algorithm, then this becomes a NP complete problem. This is the primary definition of NP hard and NP complete problem. So we'll stop this video here. We will discuss the conversion of any exponential problem L into a satisfiability problem. We'll be discussing in our next video.